Okay guys, I want you to start off with just a really quick practice of a skill from yesterday. So try this question, 2 minutes, and I'll do it alongside you. Okay, you've had a couple of minutes, let's look at it together. So we've got our two vectors, we have the dot product, so we multiply the I components and then multiply the j components. We get a bit of cancelling and then we end up with this expression here. We expand sine of 2t and then factorise out the cos, and then we have to consider these two terms. Firstly, the cos, well that equals 0 when t equals pi over 2, 3 pi over 2, etc. Then we've got the bracket. Well, can the bracket ever be 0? Well, that would require sine t to be minus 3 over 2, so no, it can't. Therefore, the first time that the position vectors are perpendicular is pi over 2. Okay, good stuff. Next thing I want you to think about, and this is the main thing we're doing today, is the idea of distance travelled, which for any trajectory is going to be a really interesting and useful thing to do. So I want you to consider how do you think you could measure the distance travelled on a plane using a trajectory like the one shown? Maybe even, if you've got an idea, pause the video and have a go at it. So hopefully if you're thinking a bit about distance travelled, that might have got you thinking about arc length when we did integration. Right at the end, for any curve, including a curve defined parametrically, we have a way to find the length of that arc, which in the same way would be distance travelled in this context. So we use that formula for our vector functions. So if you recall, if I want to work out the arc length, which I might call s, between two t values, 2 times, so a and b, well that comes out using Pythagoras as the square root of dx by dt squared plus dy by dt squared dt. And if you remember, there were a couple of different forms for this, including one that involved dy by dx, but this was our parametric form where we have a t. And because Pythagoras can be generalized to 3 dimensions, well then we can also generalize this to 3 dimensions as well, and just add an additional term in the square root if we have a third dimension k or z. Now this is pretty good, right? Because what we're saying here is for any, don't forget the dt, never forget the dt. For any any vector function now, any trajectory or path, we've got a method to work out the length or the distance of that path. So with that knowledge, try and put it into practice with this one. I've got a couple of examples today, not very much. Okay, so hopefully you pause the video and have a go, but this is quite straightforward really. We just apply this idea. We're looking between t equals 1 and t equals 3, so that 2-second period, and we want the square root of dx by dt squared plus dy by dt squared dt. Well, dx by dt, if I just look at equation here, that would be 3. dy by dt, quite straightforward, is 4. So that means this integral is the integral of the square root of 16 plus 9. So it's the integral of 5 between 1 and 3. So a definite integral moving to the right hand side between 3 and 1 of 5t, which means we have 15 take away 5 when I substitute in, so we have an arc length of 10 units, or 10 meters if it were in context. So kind of straightforward. We apply this formula we already knew in a new context and we work out the length of an arc. And then just the only other example to look at today, pause the video and just notice before you get into this one, it is a CAS question, so when you get your integral you're going to use your CAS to evaluate it. Pause the video, have a go. Okay, let's go through it. So, using the formula, same as before, arc length, this time the t values are 0 and pi over 3, and we want the square root, and always state the formula, right? If you make a mistake, then you can still get some credit for knowing what to do, whereas if you don't write it down, you're not going to get that credit. But we want the square root of dx by dt, well, sine differentiated gives me cos, so this is cos squared of t. dy by dt, well, as I differentiate this, the 2 is going to cancel with the half, so it's also cos squared of t dt, and we are going to end up, I mean, we could simplify this a little bit, but as I said, we're going to use our CAS to do it anyway. But this is the integral of, it's going to be root 2 times, as I do the square root of cos squared, I've got to be a little bit careful because I need to know that whether it's positive in this domain or not, but between 0 and pi over 3, cos is definitely positive. So it would be root 2 cos t dt, and then you would be able to evaluate this, but I want you just to practice using your calculator to work out one of these, because they might not always be so easy. And if you work it out using your calculator to 3 decimal places, I believe you get 1.061. I just want you to check that you can do that. Then part B says we'll find the shortest distance between these 2 points. So, well, what 2 points? The points where t equals 0 and t equals pi over 3. So let's work out what those are. If I substitute in 0 first, well, my location is the origin, 0i plus 0j. Now if I substitute in pi over 3, sine of pi over 3 is root 3 over 2. And then a half sine of 2 pi over 3. It's root 3 over 2 again, but then it's a half of that, so it's root 3 over 4j. What we're asking for is the shortest distance between those 2 points, and we're going to end up using Pythagoras. So, using the shortest distance formula that we learned about last time, or really, because one of them is the origin, we're just doing the magnitude of the second position vector. So it's going to be the square root of 3 over 4 plus 3 over 16, which comes out as the square root of 15 over 16. So it's root 15 over 4. And so it is, I think, on your calculator about 0.968. And let's just have a quick think before we finish about, well, what's actually going on there. We've got our origin, and then we've got this second point, which is at root 3 over 2i plus root 3 over 4j, so somewhere over here. So this point is r of 0, and this point is r of pi over 3. And what's happened here is we've worked out the distance on this curve, and I'm not sure which way it's going to bend. I'm not going to work it out, but maybe it'll bend up and across like this. And that was our part A. And that's like our path length on the trajectory. And we worked out that that red line was about 1.061. And then for the second bit, it's the straight line distance, so the shortest point and the shortest path. We worked out that that was 0.968. And yeah, we can compare them, and it makes sense to us that the shortest route is just slightly shorter than if we take an arc to get from the 2 points. So that's as much as we're going to cover just for today. This sets you up to finish the rest of that exercise, and then in our next lesson we will just look at extended review and exam practice questions before we try our next test. Let's finish off just with one more question for us to look at, just like we started. Give yourself a couple of minutes, try this one. Okay, so this is a great question, and one which tripped me up a little bit to begin with, and I think might have tripped some of you up as well. So let's have a look at it. Now they've expressed the vector in a slightly different way here, but this is neither here nor there. We can see what the components are, and there is just a slightly smarter way for us to write this, because dx by dt would be 2t minus 6. And then what I'm going to do for dy by dt is I'm going to say, well, that's going to be equal to 2 times the derivative of this. So that's 2 times 2t minus 6. And actually, dz by dt is minus 2 times 2t minus 6. Now, you might have expanded those, and you'd have had to put them back again later, but that's not so much of a problem. And so the arc length is going to be the square root of 2t minus 6 squared plus 4 times 2t minus 6 squared plus 4 times 2t minus 6 squared. You can kind of see why doing it this way works out slightly neater, because in total here I've got 1 plus 4 plus 4, that's 9. So I've got, taking it out of the square root, 3 times the square root of 2t minus 6 squared dt. And here's the thing, this expression here, we have to be careful that it is always positive, and it's going to change. So if t is smaller than 3, then this expression as written in the bracket is going to be negative, and so when I square it and then take the square root, I want to reverse the sign. So between 0 and 3, it's going to be 6 minus 2t, but between 3 and 4, as I square it and then take the square root, the expression in the bracket that way round is going to be positive, so it's going to be 2t minus 6 dt. And the way to think about this a little bit is like when we do the signed area. We're trying to integrate a function here. We want everywhere for that function to be positive. We don't want it to cancel out. And so what we're going to end up with here is 3 times the integral of 6t minus t squared between 3 and 0, plus 3 times the integral of t squared minus 6t between 4 and 3. Substituting in here, I get 18 minus 9, so that's 3 times 9, so that's 27. And then substituting in here, I get 3 times 16 minus 24. Is that right? 16 minus 24, so that's minus 8. And then take away, substituting in 3, 9, minus 18, so that's minus 9, so that's plus 9 overall. So this is 27 plus 3, which is 30, which is one of the answers. And I think that was answer C, which is correct. So the bit which requires our attention and trick is being careful with this function here and making sure it must be the positive root. Okay. Best of luck with the questions today, and I'll see you next week.